The reason we're talking about this velocity selector is because this is how physics is actually used all the time. You have mass spectrometers inside of labs, in the chemistry lab, biology lab. If you end up having a lab position, you will at some point probably use a mass spec. So this is the physics of the mass spectrometer. It is the same physics of the velocity selector, which I talked about in class. So what you do when you're actually using this physics practically is you kind of have a little box, and inside of that box, there's a little coil. You run current through the coil. What happens when you run current through a coil? What happens to that coil? What happens when you charge your phone with a wire? What happens to that wire?
It's hot.
It gets hot. So that's what you do. You run current through this coil that gets hot, and then you take some substance that you don't know what it is. You put it inside of that. That's going to heat that up, and it's going to cause electrons on that substance to jump off of it. And you take those electrons, they jump off, and they come flying out. And what you do with those electrons that you heat up from this substance that you want to know what it is you send them into an electric field. You set up an electric field with two parallel plates. I have a positive plate, and I have a negative plate. Positive plate, negative plate. And that creates an electric field. What direction does the electric field between these plates go? I see people pointing down. So that's the electric field. Okay, that's the direction the electric field goes. Now when I heat up this substance, I'm taking electrons in it and I'm ionizing it. Most atoms are neutral. By heating it up, you make it not neutral. You make it into an ion, which means it's charged. It has some free electrons, and those free electrons come flying out. Okay, so I'm shooting these particles through. I'm shooting these bits of this substance through. So I've got an ion. That ion is going to come flying through this. Ion is a charged particle. Let's say I've ionized it, I've taken some electrons off. So what's going to be the overall charge of this thing? Positive. Because I've ionized it, I've removed some of the electrons, so it's overall positive. So where is this thing going to go? It's going to go where? It's going to go down, going to go towards the negative. So it's going to move in this downward path. So this is normally what's going to happen. It's going to go down. What's pulling it down?
The repulsion.
The repulsion or the attraction. What's that called?
Force.
It's a force. What force? People are saying that I can't. There's an air conditioner right here. Velocity selector. This is a velocity selector, but what's the force that's pulling it down? Positive charge attracted to negative charge. Electric force. What's the other name for that? Do you remember what it's called? Nope, no magnetic fields here. Just an electric field right now. You're gonna hit yourselves when I tell you what it is. It's the Coulomb Force. Yeah, Coulomb Force. That's an electric force, force of attraction. Okay, so this Coulomb Force acts downward. So this force is going to move down. Fe. Going back to the very first chapter that we did all semester. Okay, Fe. So let's write down what is that force? What is the force of a charged particle moving in an electric field?
QE.
QE. Whatever the charge of this is times the size of the electric field. Okay, but that's going to make this path bend. So this charge is going to kind of arc downward. I don't want it to arc downward. I don't want it to run into my little wall. If I run into the wall of the electric field, I might break this apparatus. I want to control where this thing goes. So I want it to go through exactly straight. So to do that, I have an electric field. I can't tweak that electric field to make it travel straight through. I need to apply another force. What's the other force I can apply?
Magnetic.
I can apply a magnetic force. What direction do I want the magnetic force to go? I want the magnetic force to go up. If I have the magnetic force go up, we'll call that FB, then I can completely counteract this electric force. So my magnetic force, FB, what's that equal to? This is what Marlene was talking about earlier.
Q times V times B.
Q times V times B.
V.
Q times the velocity times the magnetic field. So I need to create a magnetic field here. The magnetic field that I'm going to create, I need it to go into the board. I'm going to call that B1, and I'm going to create a magnetic field that's inside of this whole region that this electric field is set up inside of. My particle is moving forward. So how do I know that this magnetic field has to be set up going this direction? I use the right-hand rule. I take my fingers and I point them in the direction that the velocity is going. Velocity is going this way. If I have a magnetic field going into the board, then I bend my fingers so that they're going into the board, and my thumb gives me the direction of the magnetic force. What direction is the magnetic force going? Up. Okay, so I'd have a magnetic force going up. Questions on that? Anybody see the flaw in that? V is going this way. Bend my fingers in the direction of the magnetic field. That's into the board. Thumb is pointing up. What is that? What kind of charge does that apply to? Positive charge? And is this a positive charge? Right? So what could I do to change this problem? I can give you the exact same problem. I can make that an electron, and what would change? I would want the magnetic field coming out of the board because the direction flips if I have an electron. That's something I've been known to do on exams. Literally the exact same thing. I've solved it on video. I'm solving it in class. I change it to an electron, and your brain's all right. They should. Point the fingers forward, bend them into the board would give me a proton. A positive charge goes up. If I made that an electron, I would want the velocity, bend my fingers, thumb would go down, and I reverse it to give me an electric force up for an electron. So if I change the charge, make it negative, I want to reverse the direction of the magnetic field. And I've lost about 80% of you now.
So positive and electron up.
You could do this with the IJK method as well. So IJK, IJK. I have here to figure out the magnetic force V cross B equals F, the direction of F. So what direction is V going? V is going in the I hat direction. Cross whatever direction the magnetic field is going, and that'll give me the direction of the force. What direction do I want the force to go in?
J.
I want the force going in the J hat direction. So how do I do I cross something to give me J? Okay. If I, so we had the also KJI.
Should be negative.
So if I try to use the top little section, I want to go I, and next I want something else to give me J. If I use the top, I go I, J is the only next thing I can have to get me K. I don't want that. I want I, then something to give me J. So I, then something to give me J. I times K gives me J. So that would be K. And since I'm using the bottom one, it would be negative. So I need a negative K. This is all stuff we did in Physics 1 as well. So go back and look at those notes too. Okay. So I've got this new magnetic field set up. If I want this to pass through exactly undeflected so that it just goes straight through, I need the magnetic force going up to cancel out with the electric force going down. So that means those forces have to be equal to each other. So I need Fe to be equal to Fb. This is the velocity selector QE. equals Q times V times B. And since this is the velocity selector, we solve this for velocity. So the charge cancels out, and the velocity is equal to E divided by B. So I can control how fast this thing is going. The charge of it doesn't matter. All that matters is the electric field and the magnetic field. And I can tweak those. I can make these plates bigger or smaller charges. I can make that magnetic field bigger or smaller. Literally dials on my mass spectrometer machine. Now how do we actually use this? We send all of this through this mass spectrometer and control how it enters into a region with a second magnetic field. So I'm going to call this magnetic field B2. I'm going to have B2 going into the page. So here's my velocity of my charged particle. It's going into that magnetic field. What direction is it going to arc? What direction is it going to go? Take my fingers, point them in the direction that I'm going. I bend them in the direction of the magnetic field. Fingers are coming out. What direction is my force going to pull it? Down. So this thing is going to arc downward. Okay. So I enter this magnetic field. My force due to the second magnetic field is going to be Q, the charge, times the velocity that it's going, times B2, the magnetic field in the second region. And it's doing that because there's a magnetic force that's pulling it inward. All right, I've got the velocity. As the velocity starts moving forward, it's going to be pulled down, and it's going to end up going in this arc circular path. So this FB, that's a force acting towards the center of a circle. Any force that acts towards the center of a circle is a centripetal force. So this goes back to physics 1. This is the problem with physics. It always builds on itself. So we got to remember what was the equation for force due to acceleration in a circle.
MAC.
B equals FC. FC is m times v squared over r. So our magnetic force is equal to a centripetal force. Magnetic force is Q times V times B2. That's equal to the centripetal force, m times v squared divided by r. I'm going to solve this for the radius, the size of this path. Or no, let's not. Let's solve this for what we'd actually use it for in a mass spectrometer. We'll solve it for the charge to mass ratio. So I want to figure out Q divided by M. This is what I'm looking for. How do I do that? I'll divide both sides by M first. Let's divide both sides by M. The M's will cancel out on the right-hand side, and I end up with Q times V times B2 divided by M is equal to V squared over R. What do I do next to get Q over M?
Divide V squared by V.
Divide both sides by V times B. That'll cancel the V times B out on the left-hand side, and I have V times B divided over onto the right-hand side. So then I have Q divided by M. One of my V's will cancel out, and I get V over R times B. But what's V? We already know what V is. We can control the velocity. How do we control the velocity? Think back 2 minutes.
B equals B.
V is equal to E divided by B. So I can replace that V with E over B. So I have E over B replacing that V, and then I have R times B.
Did you do that on purpose?
Do what?
BRB.
No, I didn't. Okay. So this charge to mass ratio is equal to E divided by B1 times R times B2. So in a mass spectrometer, we can measure a lot of this stuff. I can figure out the charge to mass ratio that I have from some completely unknown substance that I have no idea what it is by taking the electric field. I control that with a little dial on my machine. The magnetic field inside of the velocity selector, I control that with another little dial. The radius, I measure what that is inside of the mass spectrometer. And the second magnetic field, I control that with another little dial. This is physically what you actually do. This is how you actually use this equipment. This is applied actual physics that you use in a lab. Or at least scientists use in labs all the time. That is the velocity selector and the mass spectrometer. Okay. How else do you use this occasionally? So let's go back to this radius and let's solve this whole thing for the radius. So I'm going to get the radius over to the other side. I'm going to do that using a bunch of algebra. I'm going to multiply both sides by R, and then I'm going to divide both sides by Q over M, which is the same thing as multiplying by M over Q. So we're going to do algebra in one quick step. Cancels out our M over Q's. Cancels out those R's. This gives me what R is equal to. R is equal to MV over QB. Another useful equation for velocity selector. And we know where this comes from. This comes from doing the charge to mass ratio and calculating all of this stuff out. This is how we do problem number 57. Problem number 57 tells us we have triply charged uranium-235 and uranium-238 ions that are being separated in a mass spectrometer. The masses of the ions are 3.9 times 10 to the negative 25 kilograms and 3.95 times 10 to the 3.90 and 3.95 times 10 to the negative 25 kilograms respectively. And they travel at 3 times 10 to the 5th meters per second in a 0.25 Tesla field. They want us to know they wanted us to figure out what is the separation between their paths when they hit a target after traversing a semicircle. What does that even mean? So this is problem number 57A. We're sending these things through a velocity selector. So here's one of the uraniums, goes through. It's going to travel in an arc, and it's going to hit the screen, our detector over here. The other one, because it has a different mass, look at this radius equation. Radius is equal to mass times velocity divided by charge times B. So the mass determines how you're traveling. If your mass changes, your radius is going to change. If I have a bigger mass, I'm going to get a bigger radius. So the bigger one of these ions is going to travel in a bigger circle. And it'll hit somewhere around here. And what I want to know is what's the difference between these two? What's that distance? Okay. How do I find this out? How do I separate these two? I need to find the radius for uranium-235, and I need to find the radius for uranium-238.
You're traveling the same velocity.
Uh-huh. So what do I need to know to calculate these radii? What are the variables in the radius equation?
Velocity, mass, charge,
Mass, velocity, charge, and
magnetic.
magnetic field. Do I know any of these?
Yes.
I have triply charged uranium. What does that mean? If something's triply charged.
3 times the charge
3 times the charge of what?
of a.
What is 1 ion? Here's why I test your chemistry professors. This isn't a reflection on you. This is a reflection on Medhurst and Jaber. Singly ionized. What is singly ionized? How big is that charge? 1. We want units of coulombs.
1.6 times 10 to the 19.
1.6 times 10 to the negative 19. An ion is an electron charge. That's the fundamental charge. So singly ionized is negative 1.6 times 10 to the negative 19. Doubly ionized, what is that? 2 times that. What's triply ionized? 3 times that. Perfect. Boom. Okay, so we know the charge here. The charge is triply ionized. So charge, let's make some space. R equals M times V over Q times B. We know the charge here is 3 times 1.6 times 10 to the negative 19 coulombs. We can calculate what that charge is.
Are they both triply charged?
Yep, I think it says they're both triply charged. Triply ionized. Okay, great. You want to have some fun?
Plug that in again.
You know what's fun? Now go ask your chemistry professors if they know the physics of the mass spectrometer. So I know the chemistry of it. Do they know the physics? They might. I wouldn't ask them. They'll probably explain it. Yeah. Okay, what else? What else do we need to know? So I know what Q is. I figured out Q. Check. What else do I need to know? Give me another variable.
B.
Mass. Do I know the masses? Yeah, they told us that the mass of the ions are 3.9 times 10 to the negative 25 and 3.95 times 10 to the negative 25. Which one's which? Which one's bigger? Which one has a bigger mass?
38.
235 or 238?
38.
238? How do you know that?
Respectively. The second one has the second mass, which is the biggest.
Second one has more nucleons in it. So 238 versus 235. So 238 has to be bigger. Okay. So I know the masses. Great. So mass of 235, let's see, is 3.9 times 10 to the negative 25 kilograms. So I can plug all these things in. 3.95 times 10 to the negative 25 kilograms. So I've got the masses now. I know what the Q's are. The Q's were both 4.8 times 10 to the negative 19. 4.8 times 10 to the negative 19 coulombs. What other numbers do I need? Velocity? Do I know what the velocity is?
Yes.
Yeah, how do I know that?
They gave it to us.
They gave it to us. They say they travel at 3 times 10 to the 5 meters per second. Let's say I changed this problem. Let's say I didn't give you the velocity, but I gave you the E is equal to 5 and B is equal to 2.5 newtons per Coulomb in Tesla. Can I find the velocity from this? What is the velocity then? What was the equation for velocity? Is E over B. So the velocity would be 5 over 2.5. And I can do that in my head. That's 2 meters per second. Okay? So these are all the things I can do to change the problem just a little bit. to test if you should get an A on the exam or a B on the exam, or a C, or a D. We won't discuss the last grade here. All right. Oh, what about the magnetic field? Do I know what that is?
0.25.
0.25. How'd you know that?
Tesla. It has a D in it.
0.25 Tesla. They give it to us in the problem. So when you plug all of this in, R235 is 0.975 meters. And R of 238 is 0.9875 meters. Part B asks you an interesting question. Part B asks you, is this a reasonable size for a piece of lab equipment? Could you put this in a lab? How big is that? 0.975 meters. How big is that? About this big. That's the radius of the path that it's traveling. So how big does this machine have to be to take care of this? That's the radius. It needs to be a little bit bigger. It's about 2 meters. It's about my height. Is there lab equipment that's my height? Yeah. How big is that NMR? NMR is pretty tall, right? This is perfectly reasonable for lab equipment. We don't have it here, but yeah, you'll have it in a bigger lab. What's the separation? What's the actual separation between these radii? How do I figure out the separation? Subtract them.
Oh, that's why.
So the separation is R238 minus R235. And you find this is equal to 0.025. This is the velocity selector. It's a mass spectrometer. This is an excellent problem because it tests like everything you can possibly know about electricity and magnetism. It's very comprehensive. It goes back to the very beginning of the semester because you have to have the electric force provided by the electric field by setting up 2 plates. You have to balance that with the magnetic force. You have to figure out where the magnetic force is going. To do that, you have to use the right-hand rule. The magnetic force is equal to Q times V times B. Balance those two to get the velocity that you exit the velocity selector with. Then you have the velocity going and tracing it in an arced path, so you have to know the force due to that magnetic field, and you have to know how centripetal force is related to that to find this radius. Super good, comprehensive problem. Should you know how to do this?
Yes.
Yeah, is it going to be on the exam?
Yes.
Oh yeah, absolutely. Should you practice this?
Yes.
Yes. So practice this problem. What I want you to do for the in-class portion of it is try to resolve this yourself. Try to resolve and rederive those equations for the velocity selector. So you should be able to show me where all of this comes from. Right? You should be able to get this. You should be able to get this. You should be able to get this. So go through, try to do that. Work with each other at your tables and figure out what you do understand and what you don't understand. Things that you don't understand, write them on a sheet of paper and upload that along with your solutions for today's in-class assignment. Okay? Any questions? Anybody recognize my sweatshirt? You know these guys? Anybody watch the cartoon?
Yeah.
It's a great cartoon. It's got the best theme song ever of any cartoon, and they're making an update to it.
Oh, really?
Yeah, yeah, and it's picking up right where the last one ended. It's very exciting. And then last, I'm gonna give you a sneak peek of a magic trick.
Is that the magnet demonstration?
Watch this. Watch this. This is crazy. This is crazy. It's gonna blow your mind. It's a regular tube. That's theatrical. Nothing up my sleeves. Anything in the tube? Nothing. Anything in the tube? No. Anybody want to touch the tube and make sure I'm not doing anything with it? And a pencil. Is that a pencil? Anything weird about the pencil? Normal pencil. And then a magnet. Test to make sure it's a magnet.
Really checking.
Is that a magnet? Yes, nothing special about any of this. Nothing special about the tube. It is legit. Okay. What happens if I drop the pencil? Go through it? You sure? We can take bets? Would anybody bet money that this pencil would just go straight through? You're confident that the pencil would just go straight through. Anybody that would bet $100?
Wait. Are you using
Cheater. Huh? I don't have $100. You should see the ring that I just bought. It's yeah. I don't have the money to bet $100. But that would be a good bet because, of course, the pencil just goes straight through. Okay. Magnet. Magnet. It kind of fits in there, right? Make sure it fits.
Yeah.
Well, it's not a particularly tight fit, but it'll fit. It'll just slide right through. How do you think the magnet will just go straight through? It's like a pencil. You think it will? You bet $100. $100 that the magnet just goes straight through. Okay, that's one person that would bet $100. Anybody else? Nobody else gonna bet? You will? I want to make sure that you know that I am not cheating. So, Garmy, do me a favor. You hold the bolt. Just hold it straight up and down. Cheyenne, do me a favor. Drop that.
It's still there. It hasn't moved.
Where'd it go?
Does it have something to do with this?
The Velcro? No.
So it took longer than you?
Flip it upside down. Make sure it's not the Velcro. You do it all yourself. Drop it in.
No. But
I can see
you
it.
touch
It's gonna
it.
stay there.
What's going on?
It's gonna stay there because the Velcro's there.
Oh, it's the tube.
What happens if I drop both of them?
I was gonna say.
It's gonna take longer.
Will the pencil just pop right out?
I hope not.
It's like, well, the pencil comes out first. It's like,
Physics mystery.
It's slower.
This is 2 more chapters from now. We'll learn about why this happens. All right, work on your in-class stuff. Fun things done.
So was it supposed to not come out?
Huh?
Was it supposed to not come out?
Just comes out very slowly. And there's a reason for it. It's called induction. We'll learn more about it.
Wait, does it have something to do with the size?
It doesn't.
Okay.
Size does not
So if you
matter.
had gotten a magnet that's the same size as a pencil,
Nope,
it
wouldn't
would
matter.
still take longer.
Wouldn't matter. Still take longer. Somewhere around here, one of my adjuncts lost it, but there's another little cylinder that's the same exact size as the magnet, and it goes the same. It just falls straight through.
Oh.
You have a question?